Ever wonder how to truly see a Z-transform? We will uncover its shape in 3 dimensions. You will learn how the complex Z-plane forms the base, with magnitude and phase adding height and color. We will first define the Z-transform, then build up its 3D visualization, ending with an example. A Z-transform converts discrete time signals into a complex frequency domain, helping us analyze systems. Traditional 2-dimensional plots of Z-transforms can make it hard to grasp all their properties at once. Visualizing in 3 dimensions helps reveal the full behavior of a Z-transform's magnitude and phase simultaneously. First, imagine a flat surface called the complex Z-plane. This plane has a real axis and an imaginary axis. Each point on this complex plane represents a unique value for Z in the Z-transform equation. Next, we calculate the magnitude of the Z-transform's output for every Z value across this plane. This magnitude value then becomes the vertical height above each point on the complex Z-plane. So, we create a 3-dimensional surface, where the height represents the strength or magnitude of the transform. To show even more information, we often use color on this surface to represent the phase of the Z-transform at each point. Bright colors might show positive phase shifts, while dark colors indicate negative ones, adding another layer of detail. Critical points like poles appear as sharp, infinitely tall peaks on this 3D surface, representing unstable frequencies. Zeros, on the other hand, appear as deep valleys or points where the surface touches the Z-plane, signifying no output. Let's visualize a simple Z-transform like h of z equals 1 divided by 1 minus 0.5 z to the power of negative 1. On our 3D plot, you would see a very tall, narrow peak directly above the point z equals 0.5 on the complex plane. This dramatic peak clearly shows the pole at 0.5, indicating where the system's output could become unstable. Now, consider, how would the 3D visualization change if the pole moved to z equals minus 0.5? We've seen how the complex plane forms the base, with magnitude as height and phase as color. To visualize Z-transforms in 3D, this powerful view clearly shows poles as peaks and zeros as valleys, making system analysis much clearer. Keep exploring how these 3-dimensional landscapes reveal the hidden dynamics of signals and systems. Generate your own educational videos for free at eduvids.vercel.app.